Sorry. Okay. We are having a continuation on the last week's session, which we had a start on the probability, one of the most interesting lessons in our curriculum, as well as we are hoping to finish off the theoretical aspect as well as the past paper questions discussion by today. There's another lesson coming up which is quite adjoining to this one, lesson number 5, that is on the estimation of the confidence interval. I would say it's a very smaller lesson, and also what we are learning today has a direct relationship to that particular part with the so-called standard normal distribution. So today, students, now you've been introduced to the mean, median, and mode in our numerical descriptive measures and dispersion lesson, and we learn the principles of the normal curve and the normal distribution. Now today is a very interesting lesson. Why? It's the fact that we are going to learn how to, with the assumption of a normalized standard curve, how to calculate the adjoining probabilities. For instance, let's say you're looking at a shoe size of a particular company. The average shoe size of that particular company producing for, let's say, UK size number 7, for example. So for that standard, for that UK size number 7 standard, there may be some, let's say, by millimeters or by centimeters or by inches, there may be some standard lengths and heights and widths and so many dimensions. But in reality, students, when this company is producing these shoes, due to various reasons, that exact number will not be the number that we are anticipating. But there may be a range, plus or minus 5%, plus or minus 1 millimeter, 2 millimeter. Likewise, you may have seen in a lot of material that you see in, for example, like a cover of a particular food item that you purchase. You may see things like that. So for this shoe company also, now everybody wants to get through the perfect dimension, but due to various mechanical reasons, many other reasons, the exact output will not be there. So the standard normal distribution is going to give you a perfect answer in such instances. How can it give? It is going to define you that range, the accepted level. For example, if UK size number 7 is the standard that you're looking at, the machine will be calibrated in a way that it won't go beyond more than plus or minus 0.1%, something like that, 0.1%, very marginable amount. So that your customer will be really happy once they're wearing the shoes. They won't accept the shoe size 7 and get a 7.5 or an 8 kind of a significant deviation, but maybe something less than 1 divided by 1000, kind of a very marginal difference. So these machine calibrations, so all these output determinations, this quality checking, everything will be using the so-called standard normal distribution, with the assumption of that over thousands and millions of productions, things are going to overlapping into this standard normal distribution. So the next lesson, in fact, what we are going to learn on the next one, that is on the confidence level estimation. That is again sort of like the reciprocal of what we are going to learn under the theoretical part of the standard normal distribution. Don't worry, we will cover up the theory part on the next lesson also. But unfortunately, until the recent past papers, I think we have rarely seen that exact wording on the confidence interval estimation being applied at an examination question paper. But for the completion sake, I do believe that it's appropriate for us to formally learn that part also and wind up our discussion on the probability. Okay, so that's the part that we're heading on. And quickly, let me, so although we are on part number 2, so quickly let me catch up with you on part number 1, what we covered so far on the introduction to probability and the normal distribution. So for the first part, we had a detailed discussion on what is probability. We got a brief introduction, the likelihood of an event is going to occur, and we defined that there is something called the impossibility and the certainty. Impossibility is 0 probability and certainty is 100 out of 100. Then we moved on to areas such as definitions on what is an event, what is sample space, what is the randomness, what is a complementary event, empirical probabilities, classical probabilities, what are the differences, so on and so forth. We learned up. And then we moved on to some of these set theory, where importantly, the set theory could be uh, visually nicely elaborated by using these Venn diagrams. Venn diagrams are nothing but sort of like a graphical representation of an area-based identification for a particular group or a set. So, for example, you have group A, group B, and then there's an overlapping part of group A and B, and then there are elements which are not belong to neither group A nor B. So, likewise, you can comfortably define a set. And thereafter, we define how to add and deduct and take the reciprocal, take the epsilon minus a particular event, what is going to happen. Likewise, we learn how to apply some of these probabilistic oriented theories by using a Venn diagram. For example, P intersection B, this is middle part, A union B is going to be this whole area highlighted, and that dash, the reciprocal, is going to be epsilon or the total minus that particular area. Likewise, we understood that okay, different additions and deductions and all these functions could be performed on these probabilistic based Venn diagrams. For example, probability of A is going to be 1 minus probability A dash. B minus A, an important area, but is only related to B, could be taken as the intersection between the A dash and B. Likewise, I mean, these are not all, I mean, these are the not the only representation of these Venn diagrams. You can be creative and define whatever you want using one Venn diagram with the graphical part, and then use the notation to write it up. Okay. I just mentioned a couple of ways that you can manipulate these items like minus and dash and union and intersection, and how to represent them. The broad idea is not to graphical represent a Venn diagram, but rather to apply the knowledge coming from a Venn diagram to a practical examination question. You've seen the examination questions; those are not on highlighting areas, but rather finding a random student who is having an economic degree and being female. Likewise. So you could understand, okay, either using our very primitive knowledge on these historical tree diagrams or using a Venn diagram, you can visualize the situation and easily find an answer. So yeah, again, we understood how to put up the values or the areas to be represented in a Venn diagram, and also then calculate the probabilities accordingly. For example, if probability of A is going to be the question, A is going to be 15 plus 8, this is the whole area, divided by 50 is the epsilon. So likewise, you could comfortably give the probabilities, provided you know each and every element of these areas to be represented. Okay. Thereafter, we summarize our discussion with giving you some introduction to the rules of probability, and that is exactly where we are going to start the today's lesson. So the range of probability is going to be from 0 to 1, that is always. Summation of individual items of a probabilistic event like this, probability of x1, x2 up until xn are the entirety. If the entirety being accumulated, the probability answer is going to be 1. Area, the total area is going to be 1. That's the broad idea. And also, if you add the probability of a particular event and that event's complement, is also going to be 1. These we discuss with the visual representation of the Venn diagrams, and then we are going to formally put them so that you can learn these theories. Conditional probability, something very interesting, which we didn't discuss previously. We're being given introduction here. B given A, whatever the element which is going after this vertical line is going to be the given, or the condition that has been already occurred, or the event that has occurred previously. It has rained previously, but it's a probability that I'm going to having an umbrella in my bag. Likewise. So that conditional probability, students, you could easily calculate by using this equation. PA intersection B divided by PB. If If you try to use a Venn diagram to discuss a little bit further, this is how it is going to be. PA divided A intersection B divided by PB is going to be the A given B, and also the other side also could be calculated. A intersection B divided by PA is going to be the conditional probability of the second event being occurring after the first event has been occurred, right? So this is the so-called conditional probability. And then we were given the introduction to these independent events. Independent events are very interesting. You can't really, put up some sort of graphical representation here, but rather the broader idea is that if events are independent, that means statistically, event A is not going to have any impact on event B. Statistically, event A is not going to have any impact on event B. Likewise, if I see some dark clouds, the probability of me taking the umbrella into my bag is going to be slightly higher. So the event rain will have some sort of probability of me taking the umbrella. But something like you're winning project number 1 and project number 2, if projects are independent and if there are no conditions by the technical committees to give only one project to one particular candidate, if that is not the case, then you're getting project 1 and project 2 are perfectly independent. So what is the accumulation? What's the summation or the intersection? You can multiply these events in that case. Probability of A happening is 30%, probability B happening is 40%. So both happening at the same time. Now you can bring in the multiplication to simple as that. Okay. And then this mutual exclusive events are, this is something interesting. That means these events cannot occur, or rather no common elements between both events. In other words, PA intersection B, there is no commonality between any of these events. So if events are mutually exclusive, students, you can add the probabilities comfortably. But events are not mutually exclusive. That means you should have some sort of an intersection or a commonality like this also. That is why the case that we have these two elements and then remove the A intersection B part once. Okay. So these are the mutual exclusive events. That's where we stopped the last week's discussion. So then one could be creative and think of independent events and mutual exclusive events, and the combination. Can there be mutual exclusive events but independent? Anything is possible under the probabilistic scenarios. There could be many and multiple examples in such cases. So don't get confused. Be always specific to apply under the probabilistic rules that we have learned so far for one particular event under that particular treatment. If you're looking at a machine, a couple of machines, if you're looking at a commonality between students having a degree or a higher education, be careful and try to argue your case based on one. Don't get confused with more than one probabilistic applications at the same instances. In such cases, you may not be able to get a perfectly good answer. So thereafter, we discuss all these questions and then we moved on to part number 2. That is what we are going to learn today. Okay. So students, now this is where we are going to start. We are going to continue 2 more rules under the probabilistic jargon, and then we are going to give you an introduction to the standard normal distribution by giving a refreshing your memory on the mean and standard deviation, Okay, then that is where we are going to discuss the normal distribution and the standard normal distribution. So all these areas from area number 3 to 7, this is purely on the standard normal distribution and the respective applications. So let's get on with the today's lesson, unless otherwise you have not any specific questions to be discussed. Okay, great. Okay, rule number 7, the total probability theorem. Now this is where, in fact, by answering some of the exam questions of the last week, unknowingly we have used this theory to a certain degree. So this is where you could, put things in a formal way and learn with the name saying total probability theorem. The broader idea, without reading any of these texts, if you just look at this particular event on the blue color here, that is event number D. The total probability theorem is going to tell you, okay, given the given an event is being completely combined with the commonality of few more other events. In such cases, you can add all these individual components and bring up the probability of the event under focus. Look at this, probability of D is going to be, okay, just trying to highlight here to be more clear. Probability of D is going to be this part, that is this particular portion by this highlight. What is that? A intersection D, the common items between A and D. And I'm going to add probability C intersection D. What is that? C and D. And this other part, B intersection D. That is this middle portion. And we know, okay, either you can, keep it like this, or you can call one of these interesting theories which we learned on the last week. That is a conditional probability. What is that? It means you can rewrite probability of something like D given A is going to be probability D intersection A or A intersection D, either way, divided by P A. That is that we have learned so far. And now we see this particular event, the commonality between the D and A represented here. So you can maybe write it in the commonality way, or you can replace this by probability of A multiplied by probability of D given A. So that's why this lengthier equation is given in this way. So similarly, for all the other instruments, you can put up the conditional probability portion also, provided you know those conditional probabilities and the individual probabilities, or you can write it in the intersection phase also. So if I read you through the text, if the entire sample space is covered up by the union of a set of mutually exclusive events, what are those? These A, B, and C. These have consumed the entire space. There's a machine, and that machine, there's a factory, and there are three machines. All the production is going to come from either machine A, machine B, and machine 3, likewise. See, entire sample space is being covered by the union of set of mutually exclusive events, and those events are called mutually exclusive and collectively exhaustive events. That means the event that you're going to focus is going to be occurring from either one of these mutually exclusive events. And collective exhaustive means if you add up these individual events of A, B, and C, that is going to consume the entire sample space. The easiest example to remember the total probability theorem is nothing but this factory having 3 production line, and there's a faulty percentage and good percentage. So these areas could be good percentages, and this item, this circle, this egg is going to be the faulty. So the faultiness given B, faultiness given A, faultiness given C, you can add it up and present the total probability theorem accordingly. Okay, so more or less, you could recall that we have unknowingly used this to a certain degree by answering some of the exam questions on the last one. Okay, the last theory under the probability that we are going to discuss is nothing but an extension of what we have learned so far, that is coming from the conditional probability. Conditional probability. If you could recall, we wrote this equation P A given B, probability of A given B could be denoted by probability of A intersection B, the commonality, divided by probability of B. Okay. And you could write the other way also. What could be the case? Probability of A given B. A given B. And we all know that the top part, A intersection B, is going to be the common element. Either way, you write probability of A given B You start the top part with probability of A given B divided by probability of B. One could be getting a little confused, so let me just quickly rewrite. If you write probability B given A, this is going to be probability B intersection A divided by P A. But I just want to quickly highlight this fact. These two events, although they are written in two different ways, you can comfortably interchange these two letters. Isn't that so, students? Probability of A intersection B is the exact same thing to probability of B given A. Sorry, B intersection A. Probability of A intersection B is the exact same thing as the probability of B intersection A. So you can replace this with the same wording. So that's why here I have written both probability of A intersection B and A intersection B in the same way. Now, once you come to these placements, what's the interesting fact that you can see? You can, let me quickly highlight the interesting part, you can find a common item in both of these equations. What is that? A intersection B. Now, what you can do, mathematicians, whenever they see something common, they would like to play around with the equations. Then, probability of A intersection B, if I just use this top equation, can be taken as probability of A given B. And I'm going to take this probability B that you can see here on the multiplication to this side. Multiplied by probability B. I'm done with that. Then the other equation, this part, I can write it in the same way. What is that? Probability of A intersection B is going to be equal to probability of B given A this time, B given A multiplied by probability of A. Now, what have we done? We have written two equations, but the left-hand side of both these equations are exactly same. So, you can write it like this. Probability of A given B multiplied by probability B is going to be equal to probability of B given A multiplied by probability A. And the final outcome is that you can take one of these events to the focus. I take probability of A given B. If that is the needed one, and if you know all these individual elements, probability of A, probability of B, and one more element, what is that? Probability of B given A. If you know this, you can find the other side, the reciprocal side of it, provided you know probability of B and A. So this base rule is going to tell you nothing but that particular part that we learned previously. That is probability of B given A, sorry, A given B could be rewrote in a way that using probabilities of A, B, and A given B. So this, in a formal way, if you put it, we call it as the Bayes theorem. Bayes theorem. Okay. So the conditional probability. I mean, if you could, simply want to recap on the Bayes theory, it's nothing but a extension coming from the conditional probability theories, and also it's a derivable equation, unlike all these coefficient of variations and correlation coefficients that we computed previously, which is very hard to derive, but this is something you could logically quickly argue, and by using the conditional probability you can come to the Bayes equation. Okay, this is it on the rules of probability. There are plenty more, students, not these 8, but these 8 are the most commonly used and the highly applicable ones in the industry. So that's why we want to limit our discussion up until here to the Bayes theorems. From probability point of view, you can discuss maybe 20, 30, 50, and hundreds of different more theories, which are going to be way more advanced than these simple theories. Okay. So we are winding up our discussion on the rules on probability with these 8. And I just deliberately put this slide just to give you a quick recap on these two central tendency indicators that we learned previously. Why? Because of the fact that it's going to be applicable from this point onwards to the standard normal distribution. What are these two elements? First one is nothing but our good old friend, that is the mean, mu or x bar. Mean is nothing but you add up the values of these individual elements, add up the values of these individual elements, and then you divide it by the number of elements. That is a mean. What is a standard deviation? Given data set with n items and a mean of x bar, standard deviation for a sample and population, we know that if it is a population, we have the capital N. If it is the sample, we have n minus 1. I'm assuming, and we all know in statistics all the time we are talking about samples. So the equation for the sample part is what we are given here. So the standard deviation is nothing but the root square of the variance, and the variance part is what you see here. You have the individual x elements multiplied, minus the mu. You take the square, you add up all these individual values, and then divide that value by n minus 1, and the entire things to the power half, or the root, is going to be the standard deviation. Why do we really want to recap these two things? Is simply because of the fact that for any distribution, students, now we are going to use these two indicators to be the representatives of the distribution. You could recall we learned the curtices, the skewness, the trends, and all these patterns, and there we have highlighted, okay, for any distribution, the mean, median, and mode could be some identified, and out of those things, mean can be one of the best identified of the data set. Why? Simply because of the fact that it takes into account all the elements in the distribution. Does the mode do that? It does, but it is going to select the one sort of an extreme value which has the highest number of representation. What about the median? Isn't that the middle point? Yes, of course, that is also fine. Median, on the other hand, could be impacted by the extreme values. And the mode can be sometimes good for qualitative, and none of these elements is applicable for the quantitative other than the mean, other than the mode. So there are merits and demerits, but then again, in statistics, students, whenever we are discussing on a distribution, we take mean as the representative of that particular data set. Even for a simple thing like for a height of a class, the students' heights, are you really going to we stick with the mode or the mean or the median in that case? Typically, every time when there are quantitative elements, you tend to add all these things and divide by the number of items and take the average or the mean. So the average is going to be the starting point of our standard normal distribution discussion. Okay. So the normal distribution is going to be nothing but a bell-shaped symmetrical distribution with a mean that we are going to denote by mu. With the mean that we are going to denote by mu. What are the important characteristics? It has a bell shape, symmetrical. See, it has a nice symmetrical V, symmetrical, samanutika. This side and this side are identically same. Or you can flip it over this particular center point. And what is that central point? If it is symmetrical, we know that it is not skewed to any portion. So eventually this mu, the mean that we are going to discuss, is going to be the same as the median and the mode. If it is symmetrical, all these elements of your central tendency indicators are going to be coming to the same place eventually. But we are going to stick to mean for our discussion. And this area under the curve, what is this wording? Area under the curve. It is not a difficult thing. It is this entire area that you can highlight under the curve from the x-axis. So where is the x-axis? Is this horizontal line. And this entire area that I'm highlighting with this yellow color, this is going to be the area under the curve. And the important theory to keep in mind is that this area under the curve shall be equal to 1. How come? What is 1 and what is not? Why it is not 2 or 3 or 4? It's simple. This 1 is a symbol of 100%. And we are discussing the probabilities. So these individual x items, what are those going to be? If it is a distribution, students, these are going to be the values. Isn't that so? This is, let's say, for example, this is value number 2, this is value number 5, and then mu is 7, and this is 8, and this is 9, likewise. And what are those heights in that case? We could recall these are the frequencies. Isn't that so? I can see 2 times, 5 3 times, 7 maybe 5 times, again 8 3 times, and 9 2 times. If I write it in a some sort of a set theory, this is how it is going to be: 2 2 5 5 5 and 7 7 7 7 and 7, likewise up until 9. And then what can you see from these heights? These are the respective individual values. Isn't that so? So what is the probability of, now forget about this this entire, bell-shaped curve, and just let's focus. Okay, this yellow color area is not there, but this blue color heights are the ones that you can see. Okay, let's just think like that. And what is the probability of you getting 2? This is going to be something like, let's say this total frequency, total number of elements. I'm just putting up a fictional number, like let's say 20, for example. If that is the case, students, probability of 2 is going to be 2 frequencies, 2 divided by 20. What is the probability of 5? I have 3 number of 5s, 3 divided by 20. 7, what about 7? Probability of 7 is going to be 5 divided by 20. Likewise, students, if I add these individual elements up until, let's say, probability of 9 is 1 divided by 20, what if I add these elements? I'm going to get 20 out of 20, or 1, or 100%. Isn't that so? So that's why, students, eventually, now forget about these blue lines and think that this entire yellow items with these decimal points, 2.1, 2.2, 5.1, 5.11, like all these individual elements are not there with these respective x values. And this fx is going to be the frequency. So if you add all these elements together, that is why we are teaching you this area under the curve is theoretically 1. It's theoretically 1. Does this axis going to touch here? Not really. It's not going to touch. We are assuming that it is going to the negative infinity and the positive infinity. It's there in the next slide. I'll just quickly going to tell you the facts. And this area to the, now this is a very important and interesting theory. Look at the fourth one. Area to the left of the mu, this area. I think I better highlight it to be more clear to you. This area to the left of the mu is going to be, sorry, this part. Area to the left of the mu is going to be exactly equal to the area to the right of the mu. How come? It's simply because of the fact that it is symmetrical. It is symmetrical. If that is the case, and if this is exactly symmetrical and you can fold it with this mu line, that is the case, this area is going to be 50%, students, and this area is going to be 50%, and on the other hand this area is going to be also 50%. Okay, right. And from the probabilistic point of view, this area could be written as 0.5 and 0.5. 0.5 and 0.5. Okay. What about this lengthier equation? Do you have to remember? No, not really. This part, I really don't want to remember, but I just put it in a way to give you a brief idea. Okay. For this, now once you're engaged in mathematics, say for example, even if you put up a simple random line, you can put something like y equals ax plus b. You put up something like this, you can say, okay, y is equal to ax square plus bx plus c. Put something like this or this. Y is equal to ex e to the power x. Y is equal to 1 divided by ex. Y is equal to ln x. This is to the log power. Likewise, students, in mathematics, for any of these lines, any of these curves rather, you can denote the y or the fx by an equation. So similarly, for this normal distribution function, if you try to find out what is the curve for this function, this is the answer. This fx can be written like this also. Y is equal to 1 divided by, then you have your family of friends here. This is the standard deviation. This is 5. 5 is equal to 22 divided by 7. This is the symbol for E. E is equal to 2.713. Likewise, there's a Euler's number. It's a mathematical constant. Then you have these individual elements of these individual items of x's. What are those x's? These are nothing but your individual values, x1, x2, likewise. So what is the only replaceable part in this equation? If I just detail out a little bit for your interest, this part, you know, phi, you know, e, you know. Now these letters are constants. This mu, you know, this is the average, rho, standard deviation, you know, this is the only replaceable part. So that means, students, if you try to apply for F2, you can write all these part, and in this particular part, you can replace 2 minus mu, let's say mu is 1.5 or something, standard deviation is 0.5, something like this. And then for this part only, you can apply, and then there will be some sort of value, something like, let's say 3.71 or something like that. And that is the value that is going to come over here. This is the value 2, and this height is the answer that you just got. Okay, so theoretically, this is the complex and lengthy equation for the standard normal curve. But I repeat, you don't have to remember this part, but for the interest and for the completion sake only, I put that. Okay, right. Now we are standardizing things. Previously, what we learned is that a standard normal curve. No, this is just a normal distribution. Now we want to standardize things. How are we going to standardize? Is by giving the values to the mean and the standard deviation. Mean and the standard deviation. Now, for example, if you take the a classic example like that shoe example of that company who are going to produce. So the mean size may be 7.01, something like that, with a standard deviation of, let's say, maybe half a centimeter or 0.5 centimeter, something like that. But once you convert those values to a mean of 0 and a standard deviation of 1, you have to convert those values to a mean of 0 and a standard deviation of 1. If you can do it, and that's where only a standard normal distribution could be discussed. Otherwise, up until that point, all what we can discuss is for a normal distribution. Why do we really want the standard normal distribution, students? Is simply because of that. Then once we are doing a research, and when we have the values to apply and find the probability of an unknown territory, we can use the historical values compiled by the mathematicians by using the nice table of the normal distribution table and quickly get an answer to any of the value that we are looking for, a probabilistic answer. What's the probability of the machine is going to break down? Uh, for that, you can get an answer. What's the probability of a yogurt cup having a weight more than 82 grams? For that, you can get an answer. The weight, average weight is, let's say, 80 grams. And then the producers wants to, the manufacturers want to find the probability. The probability of the machine is going to give you a yogurt cup with a weight more than 82 grams. For that, you can apply the standard normal distribution tables and get an answer. Is that answer going to be a perfect answer? Not really, but an estimate as good as a good estimate. Okay, so what are these all the other funny curves? This is just merely to give you an example of what is going to happen if the values, if these values, mean of 0 and standard deviation of 1, are going to move from one to the other. I'm going to move from one to the other. So let's try to decompose this situation. If the mean is 0, okay, fine. You can look at these blue, red, and orange color curves. You can see all these curves are having the same mean. But we know a small courtesy question is still there to resolve. But what about this green curve? See, mu is minus 2, mean is minus 2. So that is why this curve is going to take a shape like this. Mean is minus 2. So in such a case, are we going to define a standard normal distribution? No, not really. We cannot define. Why? Because the theories and the areas under the curve that we are going to apply is going to be not constant in that case. We cannot apply. We cannot apply. But for a mu of 0, only we can define a standard normal distribution. But then again, you must be having a doubt, okay, already. If the mu is 0, what about these all the other numerical values? If the shoe company is going to produce a shoe size of 7, and you're going to tell us now the mu is going to be 0. What about 7 and the 0? That's why I told you. It is not the numerical value that has to be 0, but the converted shape. The converted shape, we are going to assume that it is going to fall in line to a mu of 0 and a standard deviation of 1. And with that assumption only, we are going to apply the standard normal distribution theory. Okay? Little further. Now, let's look at the 3 problems that we are having. This blue and the orange. The blue one that is on the top, this one, is having a mu of 0, but the standard deviation is 0.2. So the skewness problem could be seen here. Sorry, not the skewness, the courtesy problem could be seen here. The same problem could be seen in this orange color one also. Why? Mu is 0, but the standard deviation is not 1, it is 5. It is very fatty. It's very fatty. So both these curves also, students, we cannot define and conclude as a standard normal curve. Why? Because of the fact that it is either, or all three, if I take it, either they are having some sort of leptokurtic mesokurtic problems, or they are not having the mu of 0. They're not having a mu of 0. In compared to a standard normal distribution of what you are highlighting in this red color, all these other distributions are not standard distributions. All these other distributions are not standard normal distributions. This is the only acceptable shape for a standard normal distribution. For that to happen, we need to have this assumption of mu is 0 and standard deviation is 1. Mean is 0 and standard deviation is 1. Okay? Moving a little bit. Now this is how we are going to define the Z value. Z value or the Z score for a distribution, for whatever the distribution that you are having with your real values to the respective Z values. What are these Z values? These Z values are the combined between your real world values, all those shoe size of sevens and these weights of 80 grams of yogurt cups, to the standard normal curve we just discussed, to this particular shape of the mu of 0 and standard deviation of 1. All right, so this is the formula, and this formula is going to be something like your bread and butter. Why? Because of the fact that we are going to use it heavily in all our curriculum here in after. Couple of lessons actually, 3 or 4 more lessons. X minus mu. What is this X? The mu and standard deviation we know. What is this X? This is the value that you need to calculate the Z value for. So these individual X value, students, these individual shoe values of, let's say, I'll take the yogurt case example, 80 grams, 81 grams, 80.2, 81, there's outlier 85, 79.9, 79.8. Now all these individual value, students, we are going to convert it into the respective Z value. Why are we going to convert it again? And then only we can apply the theory on the standard normal distribution. What is the theory? Simply, we are going to find the probability. The area under the curve. We learn some characteristics. It is symmetrical. The left side and the right side is exactly same. And then why are we struggling a lot with these different indicators and equations? Is simply because of the fact that then only we can calculate the individual probability of one particular event is going to be less than one particular value, more than one particular value. What's the confidence interval that 95% of my values are going to be? What about the latter 20% where it is going to break? Likewise, to convert individual actual values, we use the Z value. A classic example, simple example. Let's say your data set, this yogurt example we'll take, having a average mu is something like 80. That's where we start. Standard deviation is 1 gram. This is 80 gram and that is 1 gram. And the randomly selected yogurt cup is going to having a weight of 80, 2.1 grams. 82.1 grams. For you to find the respective Z value of this particular event, you simply have to use the equation 82.1 minus 80 divided by 1. 2.1 is going to be your answer. This is the Z value. Corresponding to this particular weight of 82.1. Okay, let me take you through the notes. This formula can be used to convert the value of X that indicates any continuous variable falls normally to the standard normal variable Z. So we are assuming that it is the continuous variable and it is going to fall, or it is going to overlap into the bell-shaped curve. Any normal distributions corresponding X value shall be converted to the corresponding Z values by using this formula. So I told you, corresponding X values means these actual X values. This 82.1 grams yogurt cup, that particular value, the corresponding Z value is 2.1. That's what we calculated. This Z above is called as a Z score, which gives the number of standard deviations from the mean. Now, that is exactly what we have calculated. What is this 2.1 means? This is going to tell you, okay, this particular cup is 2.1 times away standard deviations from the mean. It's a very easy example to, unknowingly I put these numbers, but very easy to, calculate. If this is the standard normal distribution curve for this yogurt cup scenario, sorry, this this is the case. This 80 is my mean or x bar. And what about the standard deviations? And we know that already standard deviations are 1. So this is going to be 81, 82. I'm just marking 1 standard deviations and 2 standard deviations away from the mean. Away from the mean. Okay. As I guess this is going to be 79, this is 78, 77, like that. Now I have earmarks on the standard deviations also. And what is the value that I just took? This is 81.2. 80. So it's 82.1. And once you calculate the Z value also, you get the nice answers simply because of the fact that I took the standard deviation as 1. So what is this Z value is going to tell you? This is 2.1 standard deviations away from the mean. 2.1 standard deviations away from the mean of 80. Okay, that's the simple idea of Z value, but don't get carried away. There are a lot more applications of this Z value that you're going to learn in a little while. Okay, and this last point is the combiner. Now, afterwards, we shall be using this standard normal distribution table to obtain the corresponding Z value. So, any given X value to any given X value. Now, that table is the table that you can see in your exam papers in the, sorry, pull up a different paper. Something like this. In the last page of this exam paper, you can see a table which is having both sides. Let me read out it for you. It says a standard normal distribution table. Table values represent area to the left of the Z scope. And I can see this top value. It's starting from negative 3.99 to positive 0. And then from 0 to, on the next page, it goes to 3.99. So the range of this table is being denoted from negative 3.99 to 0 to positive 3.99. Although this is 3.99, logically this is like 404 kind of a, sorry, area that is given. So is it a limitation? Is it a limitation? Not really. You can define this table to more something like 5, 6, but then again the values, the probability values that you're going to get is going to be extremely tiny and small. So that's why for the computation and for the argument's sake, typically we stop our discussion with 4 standard deviations. All right, we'll see this table in a little while, but merely highlighting this fact again. So now these Z values that we just learned how to compute can be converted to the corresponding Z value table, and for any given X value, we can use that table to calculate the probability. What probability? That is what we're going to learn next. Okay, some important characteristics. The curve do not touch at the horizontal axis. It assumes that it ends up at the negative infinity and the positive infinity. So that's why I was very peculiar when I was drawing this. It is not like this. Not like this. A good representation will be something like this. This x-axis is not going to be touching. If it is touching, what is the idea? That means the probability ends there. That's the case. But for the standard normal distribution, we assume that for the negative infinity, these probabilities are going to materialize. Okay. So that's an important characteristic. The second one, the total area under the standard curve is considered as 1 that we discussed. This is based on the notion that the sum of the relative frequencies of each and every class interval of the frequency distribution being 1. That means the individual elements with the frequencies, if you add it up, likewise we discussed, it is going to give you a probability of 1. Okay, right. Now, if you look at the area, for the from the standard from the mean, and if you calculate the area of one standard deviation plus or minus, two standard deviation plus or minus, and three standard deviation plus or minus, we are going to jolly well end up with these numbers: 68, 95, 99. In fact, we are going to learn it as an empirical rule also. Let's put things into graphical ways and try to discuss. Yeah. So, how come these numbers are being calculated? Let's learn right now. What is the 0? This is the mu. What is this 1 row, 2 row? These are the standard deviations away from your mu of 0. And this dark blue area I have highlighted are symmetrical. So that's why this 34.1 and 34.1 and 13.6 and 13.6, 2.1 and 2.1, 0.1 and 0.1. So these areas are symmetrical. Okay. So the percentages that you can see here are going to tell you what the probabilities of your individual items are going to lie in between these areas. Okay. So the probability of you having a let's say 80 grams yogurt cup, and your standard deviation are calculated as, let's say, standard deviation is something like, let's say, 1 gram. That means this is the range. What's that range? 81 to 79. Yeah. Why? 80 grams is the mu and the standard deviation is 1. So 79 to 81, from the production, a total of 68.27 is going to lie in between. What about if I increase my range a little bit further? Something like this range, 82 to 78 grams. On these useful things, these are extremely useful things, isn't that so? So this is going to be 13.6 plus 34.1, 34.1, 13.6, 95% approximately 95% are going to lie from this range. And lastly, let me discuss this point. Lastly, this is 80 and this is 83. This is going to be 77. Now this is where you can comfortably see, okay, 99.73% of our production is going to be in between this range of 77 grams to 83 grams. 83 grams. And what about this 100% number? Aren't you curious? Okay, after how many standard deviations that you can see 100? There's no answer for that question. Why? We assume that for anything, I mean, even from this machine also, with let's say some weird combination, you can get a 20 grams yogurt or 100 grams yogurt. So where are those values going to be? Is it 77 and 83 going to do any justice for them? No. This 20 value is going to be somewhere over here, and this 100 grams is going to be somewhere over here. These are the outliers. Can you remember? These are the outliers. So in statistical cases, we can comfortably say, okay, fine. Still, there are room for outliers also. So that's why, students, there's no particular end answer other than this 3 standard deviation case. So we typically stop our discussion here, saying, okay, fine. This is 99.7% means only 0.3% tails are being left over. So this empirical rule of 68, 95, and 99.7% are being brought up in a way to practically apply our sales, production, finance, investments, aerospace engineering, and any of these sciences, range calculation could be done by using this 68, 95, 99.7 rule. But still, you may be getting the confusion. Okay, how do we really calculate it? This is how we calculate. Let me skip this slide because eventually it's the same thing, but I've just put up with few more data with some more advanced areas like standard deviation from the means, and then the Z scores, and then the student distribution T scores. For the moment, let's just try to quickly move on to here, and let me first show you how we calculate this corresponding Z value first. So this is the extract of that particular value that I'm taken from, could be from any of these computation. So let's say I have got a Z value as 1.02. So how am I going to calculate this particular table value? Is first I'm going to use this table, and I need to go and scroll from my vertical axis. I have to find the Z value of 1. Z value of 1. Okay, that is, we discussed there are two tables, negative table and the positive table. So this 1.02 is the positive 1.02. So that's why I'm scrolling on the positive region. Okay, I found 1. 1.0 is here. 1.0, but I have to find 1.02. So 1.02 means the third column, 1.0, 1.02. That 1.02 is his exact value that I have highlighted here. See, I look for 1 and then for 02. So typically for this exam, we're going to discuss with our assumption for the Z value of 2 decimal points. There are more advanced Z tables, and even without depending on these Z tables, you can manually calculate this area under the curve also by using theories like integration. But that's not the part that our intention is, but rather to discuss and learn the practical aspects. So once you scroll here and once you get this value, so that is where you say you are going to convert this Z value to the area under the curve. Now, what's this area under the curve? If you typically look at a table like this, for this particular value, you have got the Z value as 1.02. But that value could be something like 82 grams of our yogurt cup example. Now for this value, you know that okay, your x bar, your rho standard deviation, by using only you have come to this position. So for this 82 gram cup, you can calculate the corresponding Z value as 1.2, and by using the Z value table, you have got an answer, corresponding answer as 0.84614. What is this weird number? That's the first thing that we are going to learn. 0.84614. This weird number is nothing but the area from the left up until this point. So this is going to give you an idea. Okay, there's an 84.6% probability. I'm just chopping off the last couple of decimals. 84.6% probability that you are going to get a yogurt cup with a value less than 82 grams. You could say less than, or you could say 82 equal also. There's no hard and fast rule for the less than or equal or less than in this discussion. There's an 84%, approximately 84% chance that you're going to get a yogurt cup with a weight less than 82 grams. What about, now forget about all this explanation. What about if you make your Z to a little higher value, something like here, 84. If you do the same exercise, students, and your highlighted area will be something like this. Up until this point, we got the probability as 84%. So if you do the calculation to here, you may get a number something like 93. So always remember the fact that this is area to the left of the curve, area to the left of the curve, and that is clearly given even in the text also in your exam paper table. You read it carefully. It says standard normal distribution table values represent area to the left of the Z score, to the left of the Z score. Never get confused. The values are from both sides. All values that you're going to get is to the left. That means if you do something like, let's say, is it negative value? This is 0. These are positive Z values 1.2. And in that case, this should be something like negative 2.3. Then if you find the corresponding value, you may get something like, let's say, 13% over here. Don't forget the fact that this is also from 0 to, sorry, negative infinity to that particular value. Okay, something like this, negative infinity to that particular value. Something like this, very smaller percentage. Yeah, still that is also from the negative infinity to this particular value. That's the area that you're going to get from here. Okay. So that is how you convert your respective Z values to the area under the curve. Now let me quickly go back to this particular rule and that particular explanation. Now how have you got these possible values? That is also from the standard normal distribution curves. I mean, for example, if you calculate this particular point of yeah, sure. Can you show us an example of the negative? Yeah, sure. I'll come to that. Give me just a moment. Quickly, let me finish off this part. So, if you calculate this particular value, what's the Z value is going to be? We learned so far x minus mu divided by rho. So, this x is going to be something like 1 standard deviation minus mu is 0 divided by rho. The 0 is gone and rho divided by rho is going to be 1. So this Z value, if you look for the positive table, that should be 1.0, 1.0. Yeah. So this 1.0 is going to give me the area under the curve of 84.134. Now, yeah, like Shahan said, let's try to look for the negative value also. This negative value. I'll apply the same equation. Z is equal to x minus mu divided by rho. Now this x is negative 1 mu. Mu is 0. Rho is 1. This 0 is being chopped off. And then my Z value is going to be something like negative 1. Good example. So again, I'm using the same table, going into the negative territory. This negative 1 is going to give me a value of negative 1. From the tables, I'm going to get a value of 0.15866. 0.15866. Yeah. So now students, what we can do is that, okay, let me quickly sum up the probabilities with an approximation. This is 84% and this is 15%. So what are these two values have given me so far? I know, okay, this particular area under the curve is 84% approximately. And this, but on the other hand, this particular range is given me 15%. So that means I can eventually take up the, if I just slowly erase this particular part, eventually what am I going to get left with? This is the area under the curve for this particular 68%. Yeah. Likewise, you can apply any number of standard deviations like 2, 3, and 4 and derive the respective values. So the perfect answers, if you like really look for this 1 and 2 and 3, if you look for these exact perfect answers by using these tables, and that is how we are going to get these individual numbers of 68. Sorry, where's that value? Yeah, 68, 95, and 99.6. But then again, even if you look for these individual numbers, you may see that, okay, fine, it's not exactly 2, but 1.96 standard deviations only. You will get the perfect 95%. Perfect 95%. What's the limitation in these tables is because of the fact that it limits to our discussion to only 2 decimal places. But you can always apply the theories like integration and calculate the perfect individual exact probabilities. Yeah. So cumulatively, for example, if you look at this cumulative line, if you look for these individual values up until here, you get the 50%. For the third standard deviation, 99.9%. For the first standard deviation, see this 15.9%, I just got that value, that value. For this one, 84%. Likewise, you can get these individual numbers. So for the Z scores, if you look for individual Z scores, excuse me, sorry. This is going to be 0, and this value is going to be 1. This is this positive 1. This value is going to be negative 1. That is this negative 1 I just calculated. Likewise, your Z's are going to be how many standard deviations away from the mu, away from the mean. Okay. So this empirical notion of 68, 95, 99.7 rule is applied heavily in statistics. So this is how you calculate the standard normal distribution values and using a table. Quickly, we will look at a practical example so that your doubts and the application parts will be very much clear to you. Look at this question. Weight of a given set of people are normally distributed. Now, this is the most important thing to highlight. You cannot apply any of these theories unless otherwise the question categorically says that these are normally distributed. If they are skewly distributed or some courtesies issues are there, none of these theories could be applied. Be very careful with that. So unless given so, we have to assume and practically apply the standard normal distribution theory. With a mean of 65 grams and a standard deviations of 9. Find the percentages of weight less than or equal to, otherwise you can say less than 54, at least 80, between 80 and 86. If I just graphically put these numbers and try to find what are we targeting, this is the mean standard deviation of 9. We want the probability less than 54. At least 80. Something like this. And in between 70 and 86. Now, these are very much weird things to think that, but then again, for a decision maker, for an operations manager, quality control manager, these may be their bread and butter and day-to-day problems. Let's try to apply the standard normal distribution table. And now, since the question says that clearly you can go and assume a standard normal distribution table applies, that's why only we can apply the table. Less than 54. For the interest of time and for your comfortability, I'll just put the calculation on the slides itself. Yeah. So the mu is 65, standard deviation is 9, and the interesting value of ours is 54. So first step, we calculate the corresponding Z value. Z is equal to x minus mu divided by rho. So 54 is our interested value, 65 is the mu, 9 is the standard deviation. Negative 1.22. That's why, see, in this Z table, here move to the negative territory. So it moves on to negative 3.9 and there's a 0 here. So this negative 1.22, and for that particular corresponding value is nothing but 0.112, 0.112. So let me focus your attention here. This is the Z value, negative 1.22, and the area under the curve. Always remember, students, now in this table, there is no negative values. The table values are always positive. Why? Theoretically, an area cannot be negative. Okay, keep in mind. There's no negative answers here, but on the Z values can take both positive and negative values. If you calculate any Z value after the mu to the left hand side, your Z value is negative. If you calculate any Z values to the right hand side of the mu, your Z value is going to be positive. Simple as that. So you got this answer of 0.1122. Remember, this is the area from the left to the particular value. So now let's focus on the question. The question is going to ask you less than 54. 54 corresponding, okay, 54 is here, corresponding Z value is 1.22, and we got the area under the curve as 0.1112. That's the probability. That is 11.12% probability is the answer. Theoretically, you can put it like this: probability x less than or equal to 54. Either way, you can write it. Is going to be equal to probability of Z less than 1.22, and that is 11.12. 11.1. Okay. Moving on. The next question. At least 80 grams. At least 80 grams. At least means it should be more than 80 grams. Isn't it? More than 80 grams. Same principle. You apply the Z value first. 80 is your interested value. 80 is your interested value. Minus mu 65 grams divided by standard deviation of 9. And now we've got a positive Z value of 1.67. And then if you scroll your table to 1.67, you're going to get the value as 0.9592. Now interesting fact is this 0.9592 is not the answer. Reciprocal. 1 minus 0.9592. Why? This is the area that we want. This area that we want. At least 80 grams, more than 80. Yeah. So easy, you take the 1 minus value. How come? We have defined already saying that your total area is going to be 1. So that's why probability of at least 80 is going to be equal to 1 minus probability of less than that value. That's why we can write it like this: 1 minus 0.9592 or 4.75 is your answer. 4.75 is your answer. Okay, so that's the other side. First side, area to the left curve, easy. Area to the right side. That's also easy. The only thing to remember is don't get carried away with your quick answer from the Z table conversion. Be always careful whether you're looking for the left hand side, whether is that the area that you are going to need. And the last and the most complicated one is that in between. So in that case, if it is in between, what you have to do is, students, nothing but take one calculation between 70 and 86, isn't that so? If it is 86, for the 70, this is the first Z computation. We got the Z value as 0.56, and from the tables, we got the probability as 71.2, 71.2%. And for the second one, 86, we got the Z value as 2.33. And for this 2.33, we're going to get from the tables 99.01. And it's nothing but a piece of cake. If you know both values, areas, these areas could be added, deducted, and anything could be done. So if you have been asked to put up the values in between, that means your value has to be in between these two Z values or in between these two probabilistic ranges. That means this area under the curve is going to be the negation of these two values. Negation. You deduct one from the other. 22.78 is the answer, or you can formally put saying that there is a approximately 22 or 23% probability that the weight is going to be between 70 to 86. Between 70 to 86. Okay, so that's the third style of application. That brings our lesson to the end. Quickly recapping before the exam questions. We learned few probabilistic theories, and then we moved on to the normal distribution, and from there we moved to the standard normal distribution. That's an assumption saying that you are focusing at a perfect curve with a mean of 0 and a standard deviation of 1. If you could merge your data set, into that assumption, with a perfect shape for the mean of for the mean of 0 and the standard deviation of 1, the mathematicians and statisticians have defined these tables where we can comfortably use in our day-to-day calculations. Let's say you just take the weights or the heights of 70 students in a class and you're trying to apply this standard normal distribution. Do you think it's a good way to apply? I would still say, okay, fine. Your data set may be biased, your data set may be skewed. So the best way is that first you apply the data set, use a standard tool like Microsoft Excel, and get the simple frequency distribution table and see if it is if it is something going to be a bit more negatively skewed or having a extremely something like a leptokurtic nature. Be very careful. The theories that you're going to apply from the standard normal distribution is not going to give you a good answer. Not going to give you a good answer. So the exam questions that you're going to see from this point of view will always have the assumption saying that thousands or millions of different data is being computed, and from those data only you are taking the standard deviation and the mean for those values, and with that only you're going to take the decisions of the next batch or the next item or the next student likewise. Okay, so pretty much the feel. I think I saw a request of do another example for the both sides. Don't worry, in the interest of time, we have 35 to 40 minutes. I have picked some interesting exam questions where all these elements are being tested. There are 2 or 3 specific questions. Let us quickly, try the exam question itself, and I will show you exactly how it is being applied. Quickly recapping, what we have done so far is that either you can calculate from the tables for a value less than one particular value. It's like you have the average of 65, value less than 54, and at least 80, more than 80, or between a particular range of values, 70 and 86. Yeah. So the simple application, all the time your table is going to give you the area to the left of the curve, so that anything, something like from left to the one particular end, from left to an extreme end, if that is the case, you take one minus value to calculate the other side, or if 2 range is being given, you simply calculate the longer one first, shorter one second. Long minus short is going to give you the in-between probability. Okay, so let's jump on to the past paper questions, and there are, I think, now these are good questions. 19 September, and then you have 19 March, exact exam questions. asking all these angles. So let's try to catch up your answers over there. Okay. All right. Anything other than that? Do I need to specifically clarify before we start the exam questions? Okay, good. Guys, let's quickly move on to the exam questions because the questions are very interesting. And I always recap this fact. We have to always practice to the standard of the exam questions. Otherwise, nothing less, nothing more will help you at the exam. Okay, quickly. Now, these questions are having entirety of whatever we have discussed so far from the probabilistic theory point of view. If at all there may be one or two questions which we had discussed previous week, I will quickly skip those and share the answers. 19th September, this is a elective question, sorry, compulsory question, part number 10. A manufacturing company produces electric bulbs with 3 production lines. Line A, line B, and line C. And the quality assurance department produces following data on its quality analysis for 500 sample bulbs. 500 sample bulbs. Okay. Look at this case. 150 is coming from A, 180 from B, 170 from C. So see, there's a faulty of 10, 5, and 10 is the case. So if it is a manufacturing company, obviously, from the quality control department's point of view, whether you're accepting a bulb or whether you're rejecting the bulb is your primary focus. So out of these 500, there is a 25 faulty bulbs that are going to rework or scrap. Question: if any bulb randomly selected is faulty, given faulty, calculate the probability that it is produced from line A. Conditional probability. If given faulty, what is the probability that it is going to come from line A? Given faulty, going to come from line A. A intersection faulty and B faulty. A intersection faulty is what? This is 10 and faulty percentage is 25. So 10 divided by 25, correct? The answer is, or 2 divided by 5, any answer is fine. Answer is 40%. It's a simple application of conditional probability. If a bulb randomly selected is faulty, now the faultiness is given. So you are inside the range of faulty. Calculate the probability that it is produced from line A. Or the simple answer could be taken like 10 divided by 25 also. Yep. Okay. So simple question, simple answer. It's a conditional probability testing. Moving on to 19th September, question number 3. Big question number 3. This is actually a question on portfolio theory. So this part number 1 and 2, these all are on calculating the weighted average percentage, weighted average return, market price of treasury bonds. But this part number 3 is a direct application of what we are learning, that is on the standard normal distribution. Let me read it out. In 2019, the average return on the portfolio is forecasted at 7.5%. It is a portfolio, it's a return, that's why it is given in percentages. So average return is 7.5%, and the standard deviation is estimated at 5%. Somewhat a higher standard deviation is that. See, average is 5%, standard deviation is, average is 7.5%, standard deviation is 5%. Assuming a normal distribution describes the portfolio return in 2019. Now this is the hint. See, a normal distribution describes the portfolio. Assuming, we have to assume first. Estimate the probability that the total portfolio return will exceed 12.5%. So if you look at the case, just a piece of cake, you have to, what you have to do is bridge the ingredients. This is 7.5. What is that? That is your X bar or mu average. This is 5, standard deviation or rho. What is this? This is your interested value. This is your interested value. Exceeding 12.5. That means you will get your answer from the left of the curve to that particular value's probability. So we will take the other side, flip side. If I graphically put up this thing, now this is a great advice, students. Every time, into each and every individual time that you are answering question in area under the curve, probability and standard normal distribution, try to put up this diagram. It's a must. It's a must. Don't never try to go with the equation directly, because you may forget things. Sometimes you may forget the fact that which part that you're going to answer. Is it going to from the left side to the right side? Sometimes there may be some easy paths. If you know this particular probability up until here, you can comfortably apply the reciprocal to the other side. Why? It is a symmetrical. Likewise, so this drawing is a must. Mu, I put it as 7.5, rho as 5, and this is the interested value, x as 12.5. So first, what do we do in these cases, students? We first calculate the z value, isn't that so? Z value is going to be equal to x minus mu. This is your interested value, x is 12.5, minus mu is 0.5 divided by 5. Easy, we are getting a z value of 1. So from the table, now I don't think that I have to repeat it over and over again. I look for the table, go for the positive side, look for 1.0 and then 0, 1.00. The area that I'm going to get is 0.8413. But I know the fact that the 0.8413 is the area to the left of the curve. Up until here, 0.8413. But my focus is more than 12.5 portfolio return. More than that means 1 minus value, or the flip side, or the missing part, is going to be 15.87 is the answer. So if you put it in oral way, it's going to be, there is a 15.87% probability that the portfolio will have a return more than 12.5 in the next year, Okay. So logically, for a 5-mark question, that's the computation needed. Okay, moving on. Is another question. Again, coming from conditional probabilities and joint probabilities. This is question number 6, 19 same paper. So this will carry 5 marks. So I told you that there's typically this tendency of having one question, and that question is most of the time question number 6 with 4 different parts. Each part is going to carry 5 marks, and they will be coming from different areas like probability and maybe set theory, maybe numerical descriptive methods, maybe portfolio theory, even simple questions. So this is one such question, part number 3. Yeah. A survey was conducted among 100 youth and 100 adults to study the choices made by them in doing regular exercises. Partial results of the survey are shown as follows. So there are youth and adults, 100 adults and 100 youth may have been taken. Yeah, that's what the question says. Sorry. And there are 73 adults, 73 youngsters going to the gymnasium, and only 18 adults are doing so. While using the walking path, you can see the other side. There are only 27 youngsters, while a lot of adults are going to use the walking path. These are the statistics given. Look at the questions. Given the person is you, these words like given are going to ring a bell, sort of like a conditional probability angle. What is the probability that he selects to go to the gymnasium? Second part, given a person selects going to gymnasium, what is the probability that person is a youth? So both sides we can comfortably put it in a probabilistic oriented language like this. So the first part is asking for probability of given youth. What is the probability going for the gym? Going to gym intersection youth divided by probability youth. So this part, probability youth, 100 out of 100. Why? It's the selected subset. Given, going to gym and youth is going to be 73 divided by 100. Yeah, 73 divided by 100 divided by what is the probability of y? Now, why do I really need to calculate the probability of y? Is just for the calculation of the equation, but see the fact that it is eventually Y itself, 100 divided by 100. So the answer, first part, given the person is youth, what's the probability that he's going to the gymnasium? So eventually you are limiting your discussion to this particular area. It's 73 divided by 100, or 73% is the answer. That's the first part. But the second part is a bit tricky. Look at the one. Given a person selected is going to the gymnasium. See, now not on a territory like this or this, but on a territory like this. Going to gymnasium. Going to gymnasium. Given a person selected going to gymnasium, what is the probability that that person is you? So look at this explanation in that case. Probability given going to gym, what's the probability of that person is you? Given going to gym, what's the probability of that is going to be youth? So again, this part is same as the previous part, but probability of going to gym. Now let's try to calculate that part. Probability of going to gym means nothing but the addition of these two elements of 73 and 18, but divided by 100. Divided by 100. Yeah. So you can chop off this 200 and 100 easily, but it's not like 73 divided by 100 anymore, but 73 divided by 73 plus 18. 73 plus 18. Look at this part carefully. Not that going to gym is 100, but rather it's 73 adults and 18 adults and 73 youngsters. Yeah. So answer is 73 divided by 73 plus 18, 80.21. 80.21. Or without any of this theory, you can argue from your common sense also. Given the selected person is going to the gym, what's the probability that that person is you? This is the total chaps who are going to the gym. 73 plus 18. Out of them, 73 are you. Likewise, also you can argue and resolve. Okay, that's another question. All right. Now this is the answer for some more examples of the application part. 19th September question number, same question, the next part number 4. Rice bags are manufactured to a specification of 10 kg weight and issued to the market only if they are within the range of 9.9 to 10.1. See, 10 is the 10 is the expected weight or the average, but they are not issued to the market if it is more than 10.1. But if that is the case, the producer is making a loss, right? 100 grams more. If it is less than 9.9, then the consumer is making a loss by 100 grams or less. If the weights are normally distributed with a mean of, see this is the case, are normally distributed with a mean of 10.05. See, although you are anticipating it to be 10, the actual is going to tell you a slightly different story. 10.05 is the actual mean. And a standard deviation of 0.05 kilograms. Compute the following percentages of rice bags which will not be issued to the market. As A, underweight, or B, overweight. A, underweight and B, overweight. Let's look at the answer. This is the case, graphical representation. So first, we write the things that we know. Mu, what is this? This is the average. Rho, standard deviation, 0.05. Standard deviation. And this x1 is the range for underweight, 9.9 kilograms. And x2 for the overweight. x2 for the overweight, 10.1. And what do I need to do is to calculate the probability of individual elements that will not issue to the market due to A, underweight, and B, as overweight. Okay. So the underweight percentage, PU, I just put as some symbols, PU is going to be 9.9. Now this is the value for the underweight margin, 9.9 minus 10.05 This is the mean divided by 0.05. This is the standard deviation. And the answer I'm going to get is negative 3.00. Negative 3.00. If I do the same thing for probability of overweight, 10.1 minus 10.05 divided by 0.05, positive 1. Positive 1. And if I use my tables and apply for the individual elements, I'm going to get as this negative range as 0.00135, negative 3. Or the probability answer directly, I can get it as 0.135% of rice bags will not go to the market due to the underweightness. Due to the underweightness. And what about the overweight range? Now this one, the answer that I got, 0.84, is this the answer? No. Why? This is area to the left of this curve is the 0.8413. But I'm looking at the flip side, other side. That means 1 minus 0.8413 is going to be my answer. Or in by words, if I say it, there is a 15.87% rice bags which will not issue to the market because of the fact that they have been overweighted. They have been overweighted. See application of both sides, under and over, under and over. Yep. Few more questions. Quick recap on what we learned last week. A yogurt factory, 5 production lines. On past evidence, there is an independent probability. See these important words, independent probability. The examiner has made our lives very easy. We don't have to think rationally. Independent probability of 2% breakdown of any production line each day. The probability that there will be no breakdowns on a factory is, this is the answer, right? 0.98 to the power 5. Yep. I hope you can recall the answer is D. Quick recap. This question, I think we discussed last week also. Factory produces 80% of the items in A, there's a 5% faulty, 10% faulty in the other side, B. I think this is a repeating question, sorry about this. And so there's a probability of faulty as 6%. We discussed the same question last week, sorry. Okay, now these are those couple of good questions that I mentioned. A machine produces steel rods with a diameter of 40 millimeter, and these are used for automobiles. The actual diameter of rods varies, being approximately normally distributed with a mean of 41.2 and a standard deviation of 0.8 millimeter. What are these values? This says, okay, fine, although we are anticipating the diameter to be 40 millimeter, but the actual mean is 41.2 and the standard deviation is 0.8. Okay. Look at these questions. First one, calculate the percentage of rods whose diameters is between 40 to 42 range. We'll discuss question one by one, otherwise it's a bit more text. First question we will try to resolve first. Calculate the percentage of rods whose diameter is between 40 to 42. First part, I invite you always to do this. Do the simple diagram. Mu is 41.2, standard deviation is 0.8. This is the expectation. They want the range. They want the range between 40 and 42. Between 40 and 42. Easy. We calculate the first Z to 40. 2. That means 42 minus 41.2 divided by standard deviation. My Z value is 1. The second value for Z 40. I do the same thing. 40 minus 41.2. I'm getting a negative value now. Negative 1.5 is the Z value. And from the tables, if I look for the area under the curve, for the first area, this area to the left of the curve, I'm talking 42, is 84.13. And the second area, the small area, I'm getting as 0.0668 or 6.8%. The delta or the negation is the answer. The range is going to be 77.5. If I quickly put up another diagram just to be more descriptive, 84.13%. minus 6.68%. That is this range that I'm going to get this answer. Okay, that's the first part. Second part, 20% of the rods with the lowest diameters are rechecked for their quality. Rechecked for their quality. Lowest diameters. Huh? What is the approximate cutoff diameter to select the rods for rechecking? That means this 20% number is established. We don't know what's the diameter for this margin. That's the question being asked. All what we know is simply to put things in a diagram. We put things in a diagram and this is what we can realize. So there has to be some diameter saying x, which we don't know that value, but after that diameter, this area under the curve has to be 20%. I just apply these values. I can calculate Z value saying x minus 41.2 is my average divided by standard deviation of 0.8. But from the table, now this, if I calculate Z value, I should be getting a value, but from the table, I can now reverse engineer. How can I do it? I can use the tables and go for what's the area under the curve. The 20% stands for 0.2, right? So what's the area under the curve from the negative range to get the value of, the question says it's from the negative range, to get the value of this 0.2. If I do it manually one more time, I'm going to get 0.84. 0.84 is going to be the answer, 0.84. So if I exactly look for the 20%, I can't get a number, but approximate number that I'm going to get for 0.84 is calculated as something like this, 0.20045. Or this is going to be equal to something like 20.045%. So this and this are the values that I just equated. Theoretically I can calculate the perfect Z value, but with the table, with the 2 decimal limitation students, we are having no choice but rather to be limited our approximation to the most approximate value. So that's why I use the table. I reversed engineered. Okay, I know if I calculate the Z value, I have to get 20%. So for that 20%, my respective Z value is going to be nothing but the 0.84. That's how I got here. Now once I got here, it's a piece of cake. I just need to find the value for x. I multiply 0.85 with this value, and then I take the 41.2 to the other side, and I'm going to get x as 40.53 millimeter. And if I just vocal it, I can say, okay, to identify this the lowest 20%, the lowest 20% of the production to go for the reworking, I have defined my cutoff diameter as 40.53 millimeter. My average is 41.2. So if there is a when I actually measure this using a vernier caliper for the not for the millimeter, and when I really find that, okay, if a rod is less than 40.53 millimeter, I have to quickly resend it to the rechecking. So that threshold is being established. That threshold is being established as 40.53 millimeter. That's a good practical application of the standard normal distribution. Third part. All rods of diameter more than 42.5 millimeter are not issued to the industry and recycled at the company at a cost of 50 per rod. Calculate the approximate recycling cost associated with producing 1000 rods. All what I know is, all the time, I put things in a diagram. I put, 42.5 in the diagram. This 42.5 is the point. Now, if you would recall that in the previous instance, students, if a rod is less than this 40, sorry. If a rod is less than this 40.53, we just send it to the reworker. Sorry about background noise. So if this particular rods are now more than 42.5 millimeter, now we are going to recycle it. So, I think some celebration is going there for some. Okay. Now this 42.5%, sorry, this 42.5 millimeter margin, if I can calculate, okay, what is the percentage of approximately production is going to be more than 42.5, what can I calculate is the fact that simply, okay, what's my recycling income or the cost is going to be. So simply, I just apply again the Z tables by calculating the Z value. 42.5 minus 41.2 is my average divided by standard deviation. I'm going to get the Z value as 1.625. From the tables, I get the value as 94.7%. 94.7% is this area. The other side is 5.2%. So what is this? What is this 5.2%? That means approximately there is a 5.2% production of rods going more than 41.2 millimeter. Sorry, 42.5 millimeter. Yeah. So if there are 1,000 rods being produced, that means out of these 1,000, 5.2 are going to go through this cycle, out of this cycle, with a cost of 50 rupees. And if you multiply all these elements, you're going to get 2,600 rupees as the cost associated with this business. Calculate the approximate recycling cost. That means approximately 2,600 rupees that the company has to bear for the recycling work of the diameters getting more than 42.5 millimeter. Okay. See how many different practical angles that one question can test. Last one. This company decides to change its production process to reduce the percentage of oversized rods to be recycled at 1%. Keeping the standard deviation unchanged at 8 millimeter, what adjustment should be made to the mean diameter of the rods? Okay, this part again. The company has decided to change its production process. Why? Simply because of the fact that now the wastages they're not very happy with. They want to reduce the percentage of oversized rods to be recycled to 1%. We just previously calculated, okay, there's a oversizing and there are certain percentages of rods are going away. Keeping the standard deviation unchanged, keeping the standard deviation at 0.8 millimeter, what adjustment should be made to the mean diameter of the rods? That means you calibrate your machine and the average will be slightly moving from one side to the other side. This time also, I just put all these things in a small diagram first. So what I know is, I don't know the mean right now. X bar unknown to me. But I know, okay, by referring to question number 3, the oversizedness is defined at 42.5 millimeter. Okay, this part again. All rods diameter more than 42.5 millimeters are not issued to the market, so and so these are oversized. So this question number 4 is having a nice relationship to the question number 3. Assume now we have to assume that, okay, fine, this oversized business will start at 42.5, otherwise we can't resolve this question. Yeah. Now this is the this is the locking point, and we know that this has to be limited to 1%. So this is 1%, and this probability has to be 99%. So I know that X bar is being kept as the unknown, but luckily standard deviation cannot be changed. Why has the examiner said so? If you have another unknown here, you can't resolve this question, students. Yeah. So 42.5 minus X bar divided by standard deviation is going to be equal to 2.33. Where this 2.33 coming from is simply because of I have directly taken from the table what's the Z value for 1% or 99% here. 99% here. Okay. So X bar is going to be the simplification of this particular question is going to be X bar, if I put it to here, and this 42.25, I'll keep it here. This 2.33 multiplied by zero point 0.8, I'm going to take it to the left hand side, and my answer is going to be 40.63 millimeter. What's his answer? If I put it in words, if I convert the machine's output, the X bar, to 40.63 millimeter, 40.63 millimeter, and then I can limit the oversizing to 1%. I would recall this question as one of the best questions being tested, all the possible angles from the standard normal distribution. Okay, any unclear areas? I can still be at your disposal on this particular question. Okay. Okay. There are a few more questions. Kindly bear with me. I think with this we can wind up for the entire session. So we'll quickly try to calculate the other questions also. This is 19 marks, question number 6 for 5 marks. It's asking some expected calculations. Fast food company, 2 types of mobile vans for outdoor events. We have seen these many vans and these ice cream vans, Highland. Sorry, not Highland, these Balls ice cream kind of vans in these different event outlets, like book exhibitions and all. The daily profit of each of these van depends on whether the pattern, depends on weather pattern. And on its past experience, the company predicts the following daily profits. Look at these numbers. If it is a rainy day, if you take the ice cream vans, obviously it's going to be a huge loss. Why? You have profit from that van. If you, what about if you take cup noodles? For a rainy day, everyone will like to go for a nice hot Maggi noodles cup or a different brand. And even if it is a fair day, there will be a positive 1,000 rupees profit. Now, this is what we know from the previous experience. First part, company plans to attend an outdoor event in 2 days' time, where there is a 60% chance on rain and there's a 40% chance on a sunny weather. Which van should the company take to this event? Justify your answer. Second part, if weather forecast change to 30% chance of rain, which van should the company take? Now, each of these events, student, we can comfortably calculate the expected values. What are the expected values? From probability, you can calculate the outcome by the probability and then get the expected probability. Sorry, expected value from monetary point of view. So the first part, if I explain, there's a 60% chance of rain. There's a negative 5,000, sorry. And then there's a 40% chance of not raining and 15,000 profit. If you multiply these numbers and add it up, the expected profit of ice cream van for the first scenario is 3,000. But if you take the noodles van, 60% rain, 12,000 profit, 40% no rain, 1,000 profit, the expected profit is going to be 7,600. So that's why, because of the expected profit is higher, we are going to take the noodles van. But what if the forecast changes drastically? The 60 is going to change to 30. Drastical change. If that is the case, students, these other values, these 5,000s, 15,000, 12,000, 1,000, they remain same. But the 60s and 40s has now converted to 30s and 70s. If that is the case, these are the final profits that we're going to see. And now you can see the profits has converted it to the flip side. The ice cream van is making more profit now. And if that is the case, we are going to take the ice cream van and not the noodles van. So the justification part, the broader idea is that what you have to do is you have to say the justification, the expected profit, the maximized expected profit is your decision making point. Okay. Right, moving on. Now this question I think has been discussed before, but for the completion sake. Group of 100 undergraduates, 40 are males, 60 are studying economics, 16 of the males undergraduates are not studying economics. Something like this. So you put up the question, the green color text are ones that I have calculated later. 40 male, 60 female, we know. 16 are not studying economics. So that means 24 should be the other. 65 students are studying economics. That means if this is 24, 41 students must be female and studying economics. And if this is 41, we can, this is 41, we can calculate, okay, this should be 19 for the female total to be 60. Yeah. So once you have all these areas been defined, then you can answer any probabilistic question coming from any angle. First question, an undergraduate selected randomly is female. Is female in this territory. What is the probability that she is not studying economics? 19 divided by 60. 60 is the territory. 19 students are not studying economics. 19 divided by 60 is the answer. Look at the second question. Calculate the probability that a randomly selected student, undergraduate, will be female and studying economics. Will be female and studying economics. Now, in that case, we are talking about the epsilon entirety. Will be female, 60% chance, and studying economics, this smaller area. Focusing on this area, this is going to be 41 divided by 100. Yep. So different angles, common sense, tree diagrams, or Venn diagrams. Anyone you think is more comfortable at your disposal to use. But the clear explanation should be written in Word for the 5 marks to be attained in full. This question I think we have tried previously. Just straightforwardly put up the answer. 45% employees have a degree in economics, 45 to 55 deviation is coming from there, and 60% have degree in statistics. So 60% out of these econ graduates must be having a stat degree and 40 not having stat. Similarly, on the non-economic students also. What's the probability that an employee chosen at random has a degree in economics or a degree in statistics? That means either a degree in economics or statistics. So what I have to eliminate is non-economics and non-statistics. Yeah, non-economics is 55 multiplied by 40, that is 22%. So if I just eliminate this portion, 78% is the answer, part number A. And a similar question we have tried in a different paper last week. Yeah. 18 September, bear with me for a couple of more minutes. These are few more interesting questions. And now this is a yogurt cup example. Dairy production company produces set yogurt cups whose weights are normally distributed with a mean of 80 and a standard deviation of 1.5. Set yogurt cups, mean of 80, standard deviation of 1.5. And again, they're discussing about another machine. What is that? This company is planning to buy a new machinery producing fruit yogurt cups. Testing. The specification for the new machinery states that the weights of the fruit yogurt cups are normally distributed with that 11.5 cups weighting over 80 and 5.9 weighting under 78. If I put it in a graphical orientation, the mu and rho are not given here, but the calibration portion will be given here. 11.5 will be over 82, 5.89 will be under 78. Okay, that's all it's given here. Two machines, set and fruit, two machines. Another good question testing all the angles of your probabilistic knowledge. First part. What is the probability that a set yogurt cup chosen at random weighting less than 75? Focusing on the set yogurt machine. Piece of cake. We put the ingredients in the picture. 75.5 is the value of interest. Z is going to be equal to 75.5 minus 80. Where is 80 coming from? This is the average of the set yogurt machine divided by 1.5 standard deviation. Z is negative 3 from the tables. My answer is 0.135% probability is there that a set yogurt cup chosen at random weighting less than 75.5. Okay. Second part. All set yogurt cups weighing less than 75.5, and that part we calculate, are not issued to the market. They are given to the company's welfare shop free of charge. Welfare shop sells these yogurt cups at 20 per cup. if company produces 500,000 set yogurt cups per month, and then welfare shop sells only 96% of these yogurt cups, calculate monthly profit that the welfare shop could be earning from selling these yogurt cups. Now you must be bit careful to go to a welfare shop of a producer thinking that they must be doing this business. But it could be a rational case, isn't that so? But if a cup is going to the market at, let's say, 30 rupees, but with a slight deviation of a few grams of deviation, if they cannot be issued to the market, why not give it to the welfare shop, do some welfare to the employees, and sell it at a reduced price? So it seems to be a logical thing for me to do. A simple calculation: if the company produces 500 set yogurt cups, what's the percentage? 0.0135, the previous question. That number of yogurt cups are going to be get to the this particular welfare shop. And there's another catch: only 96% of such yogurt cups could be sold, while it's a perishable item. 4% will go beyond the expired date, so you can't sell it. Scrap, gone. Calculate the monthly profit of the welfare shop. So this, I think, this 20 rupee, since the welfare shop is getting at free of charge, we have to assume that sell price is going to be the profit. If that is the case, 500,000 is the production, this is the faulty, this is the sales, and this is the price, and I'm assuming it's the profit. If you multiply all these elements, there is a 500,000 production and 0.135 faulty. 96% of them will be sold at a price of 20 rupees, and the welfare company can make 12,960 rupees as the profit. And now we are coming to the fruit yogurt machine business. Calculate the mean and the standard deviation of the weights of the fruit yogurt cups to be manufactured with the new machinery. Now let's try to, we know that this is being given, now we need to calculate the missing two pieces. I just put this in my usual diagram. If I write for the first point, this is 82 grams. I don't know M, I don't know rho, this machine. I just given the calibration points only. 82 minus M divided by rho should be equal to 1.2. Where is this 1.2 coming from? This is coming from this particular region from the tables. Similarly, for the other side, 78 minus M. So be careful here. You don't take M minus 78 just because of the fact that this is lower. Always you take the application of the equation. X minus mu, not mu minus X. 78 minus M divided by rho is going to be equal to negative 1.57. This is the corresponding Z value. Once I am here, students, I can jolly well find, okay, there are two simultaneous equations that I can resolve. 82 minus M is going to be equal to 1.24. 78 minus M is going to be equal to 1.57 rho. You add these two equations together, M will be chopping off. 2.77 rho is going to be equal to 4, and I'm going to get a rho, that's a standard deviation of 1.44. And if I apply it to any equation, I can get the mean of 80.22. If I voice it, the fruit yogurt machine will have the mean weight of 80.2 with a standard deviation of 1.44 grams. That's on the part number 3. Part number 4. Calculate the coefficient of variation. What is this? Previous lessons, yeah? Coefficient of variation for these two machines which produces set yogurt cups and fruit yogurt cups. What can you tell about these two machines from your answer? Coefficient of variation. I'm sure my good students will remember the equation. Coefficient of variation is not a very difficult thing to remember. It's the fraction of the standard deviation divided by the mean. For these two machines, now I can calculate the coefficient of variation by 1.5 divided by 80, and this freshly calculated 1.44 divided by 80.26, and I can see F is less than S. And we have learned under the coefficient of variation theory, if the higher the number, higher the variation. So how I can conclude saying that fruit machine is more accurate. Why? There's a less dispersion compared to the set machine. Fruit machine is more accurate. The output is more accurate. Why? Lesser the variation. Marginal variation, but lesser. Okay. See the number of angles one question can test at the examination. Okay. In the interest of time, I think this is a pretty much similar question. Quickly, let me share you the answers for the two lines, number of books accepted and rejected. First part, calculate the probability that a random selected book will have been manufactured on one and having rejected. First and second part, calculate the probability that randomly selected book will have been manufactured with the accepted quality. So 60% line 1, 40% line 2, 88 is going to be accepted from line 1, 12 will be rejected in that case, and 6 and 94. So the first answer is going to be 60 into 12. The fault is coming from line A, is the answer is 0.072 or 7.2%. And the second part is random selection will have been manufactured by with the accepted quality. It means both good sides, 60 good, 60 into 88, 40 good, 40 into 94. The answer is 90.4%. Expected values, tree diagrams are the easiest one way to calculate. Okay, that brings me to the end of our discussion on this long probability theory standard normal distribution. I can still be at your disposal. I think the questions are somewhat challenging, I would say, but merely we are only playing with this one particular equation on the Z values. The correct application, I'm sure you have to spend a lot of time on scrolling your fingers in between the uh, table. Try to be familiar with this table, students. Now, this table is the only table that is on the last page of your exam paper. No equations are being given so far. We're not sure whether if the examiner can be merciful in an upcoming exam and give you some equations. But since it is been not clearly mentioned in these previous papers, we're assume that you have to keep in mind of the equation. But this table is the only table that is being given. So you can comfortably be ready for the application side of it. All right. So I can still be at your disposal if you have anything to discuss. And the next lesson, we will discuss on the confidence level estimations and the application side of it. Okay. So if there are nothing to be discussed, so I can wind up for the day. As always, if you have any questions, you can drop me in the IBSL email. Okay then. Shall we wind up for the day?